Okay, we're going to take a look at the design capacity, and we're going to look specifically at the Hunter guide to help us calculate the initial available system capacity, the static pressure and the estimated dynamic pressure that we might have to get us going on our irrigation system. Take a look at the diagram. This is actually figure 21 from the Hunter student guide manual, and you can see your city water source is down here, and that's where you might connect. Coming from that, you would go to the service line, and the service line might be right along here. If you did have a curb stop, it might be somewhere in between here, between the meter and the rest of your irrigation system. You know, we often put an off valve associated with the pressure reducing valve and with the backflow preventer that would be at the point of connection to the house, but sometimes we forget about the service line that would be going from the meter to the house. Now, it may be the same service line that would supply the rest of the house. In that case, it doesn't really matter. You can always shut the meter off. But I have actually installed a lot of irrigation systems that ran on a separate line to get additional capacity from the meter to a different place where we were going to have the point of connection. The other thing you want to look at is the water meter. And of course, most of us are used to looking at water meters. That's usually very close to the property line or somewhere where the city can take a look at it. Sometimes it's buried very deep. I had one when I was living in Utah that was probably the point of connection for me to run to the house was about 5 feet deep. And the water meter was above that, but to tap in was below the frost line to protect it. Then we have the service line coming up to the house, and we come up to the point of connection place that we might actually tap in our irrigation system. From this point on, the other thing we want to notice here is that we do have the highest predicted level of the irrigation system, and we're going to add that in just a minute to calculate our estimated dynamic pressure with the worst case scenario for the dynamic design that we need. And so here's a couple of definitions that we want to go through real quick. The design capacity, that's going to be the amount of water that's available for use. That's going to determine how many sprinkler heads or how many drip lines or how many laterals we can connect at the same time. For an awful lot of our household systems, we're talking something in the range of anywhere from 12 to maybe 25 gallons per minute. You know, if we don't have anything else to estimate that, a lot of times we'll just use a hose bib and we'll open it up and we'll see what kind of flow we get out of a hose bib. Now, that's not the best thing to do because a lot of time the hose bib is necked down to 1/2 inch or 3/4, and maybe your actual line coming to the house is much larger. But if you don't have any other easy way to estimate the system, that certainly is one thing a lot of homeowners can do without a lot of additional work. The dynamic pressure is known as the working pressure, and that's the amount of available pressure that we can have to calculate while the water is flowing. It's real important that we realize the static pressure we can measure by attaching a gauge to the hose bib, but we cannot get the dynamic pressure unless the water is actually flowing at capacity. So the dynamic pressure at design capacity is a calculation of the pressure that's going to be available at the maximum system flow rate. So it doesn't do us any good to have a static pressure of 65 PSI, and then when we turn it on, the actual dynamic pressure at design capacity drops down to 45, and then we design our system for 60 PSI because it's just not going to work. So we got to make sure we check all the available information. The other thing is the flow, the volume that we're going to get in either gallons per minute or liters per minute, or it could be in cubic meters per hour. These are municipal systems that we're used to talking to, so it's going to be a little bit different for us. The dynamic pressure at design capacity, we already mentioned, that's going to be an estimate of the dynamic pressure for the worst case head of the 3 most common landscape irrigation water sources. That's what we've got listed, at least in this particular worksheet. And those are going to be metered municipal, unmetered municipal, and pumping from a well. And we get into that with quite a few rural systems. Well, here we go. We're going to start talking about design capacity. I went outside and dug up my meter so you could see what it looks like. And some of these are buried and have a little cover. And they might also, more than likely, look like something like this nowadays. And you might see that it's hooked up so that it has actually can be read electronically, and most of them nowadays are actually they're able to read without even hooking up to anything. They have they can read them with a meter that doesn't require any kind of connection at all. It's done by the truck as they're driving by. First thing we need to do is to calculate the design capacity with the static pressure. The static pressure where it comes in to the point of contact. Now, we can either measure that if it happens to be available, or if it's not available, sometimes we can call the city and ask them to provide it for us. Most of the time I found that I've had to just simply go to a hose bib at the house and measure. So in this particular picture, if we had a hose bib sticking out of the side of the house right here, and let's say that that elevation was 5 feet greater than our point of connection A, we would have 5 times, if you take a look at this sheet, 5 times the elevation change, and you know this already from the class, is 0.433 psi per foot. So 5 times 0.433 feet is going to be pressure per foot is going to end up being just a little bit over 2 psi. It comes out to rounded about 2.2 psi. That means we can expect there to be a couple of psi difference between here and our point of connection. So if we attach right here to the hose bib and we measure 68 psi, we could expect the available static pressure be somewhere around 70 psi. Now in our example, we're going to just call the city and we're going to ask them. We're going to say, what is our line pressure? And they're going to tell us it's 85 psi at the water source. So now we have a static pressure that we can use to calculate the rest of our system. So we're going to go in here into our design sheet and we're going to put static pressure of 85 psi. Now we need the net elevation change sourced to the point of connection, either uphill or downhill. So let's go back to our drawing here, and according to our example problem, we have an elevation gain of about 12 feet up to the meter and about another 5 feet after that. So we're going to have a total of 17 feet. So the net elevation change is 17 feet. You would just fill this out the same way for any system that you're working on. The pressure change then is going to be 17 times 0.33 in this particular case. That's going to equal the pressure change of 7.36 psi. The static pressure then is going to be 85 minus the 7.36 to give us a static pressure that we can actually start our working with at about 77.64 psi. Now that's the theoretical psi, and of course that's going to change depending upon when you measure it, what's running. You got to make sure that nothing is on in the house, that you have no water running anywhere in the system, and you want to make sure that you measure that when the irrigation system is likely to be running. Most people find that the irrigation system demands that if everybody in the neighborhood is working at the same time are going to be quite heavy, and you may see 10, 20 psi drop. I know in one particular case In one house, we measured somewhere in the neighborhood of about 30 psi drop, and the reason we had 30 psi drop is the two houses that we were looking at were interconnected, and they were both running off of 1 meter. So that meant even though the one house wasn't using it, the other house was, and it made the irrigation pressure that was available for irrigation fluctuate greatly. All right, the next step is we need to actually have some information from the system itself. We need to know the service line, the delivery line, the water meter, and any other valves that we have. So let's go back to our drawing, or back to your actual system if you can, and take a look at it. In this particular case, we have a service line down here that is 25 feet long, and it also happens to be 1 1/4 inch copper. All right, and that's something that you can actually measure. Next is the delivery line. The delivery line is PVC, Schedule 40 PVC. It's also 1 1/4 inch. And the length of that is 65 feet. Finally, we have the water meter, and the water meter in this problem is going to be a 1-inch water meter. And usually you can find that information right on the meter itself. And if you remember in this example right here, if you can see this, that's a 5/8 inch water meter in this particular case. So it's usually stamped somewhere right on the meter itself, so that you don't have to figure out what that is. And in this particular case, we don't have any other valves until we get to the point of connect. So we just need to fill in our data. The service line we said was going to be 25 feet, and the size was 1 1/4, and it was going to be copper. The delivery line was 65 feet, and it was also 1 1/4, and it was Schedule 40 PVC. And then we had a 1-inch. Just write it down here because it's a little easier to see. Meter. The next step is to determine the design capacity, and there's 3 different rules that they go through in both the Rainbird and the Hunter manuals to simplify this process. And the first one is pressure loss, and we want to take a look at pressure loss through the water meter, and we don't want that pressure loss to exceed 10% of the available. So if we go back to the meter, we need to look that up and find out what the available amount of pressure loss that we can have. And in this case, if we measured 85%, and we can use tables like this as well, but this is calculated here as just 10% of the the static pressure at the main. So 10% of 85 is 8.5 GPM. Okay, we're going to take a look at the volume through the water meter now. And the water that is not to exceed 75% of the maximum safe flow for the meter. So we go back to that table that does the pressure loss through the meter, and I've got one here that I printed off. This one's from Rainbird, and there's one in the Hunter manual. You can't quite see it when I printed it off. It chopped off a little bit down here, but if you follow this through, or you look up any pressure loss through water meter chart, and it'll give you the same kind of answer. For a 1-inch pipe, 15 psi at 50 gallons per minute. So what we want to do is we want to come back here and we want to take 75% of the maximum safe flow of the meter, and since it finished off at 50 gallons per minute, we want to take 75% of 50 gallons per minute, and we're going to come up with about 37.5 GPM. And then our third rule is the velocity through the service line, not to exceed 7.5 feet per second. And we already know that in a lot of our systems, if we had 7.5 feet per second, we could get water hammer. But in this particular case, that's where we want to draw our design limitation. So let's take a look at a design chart here for friction loss, PSI loss per tube for copper water. And let's go down for the 1 1/4 size that we have. The velocity in feet per second, drop down that table till you hit something in the neighborhood of 7.5, which is less than this one here. So we've got 7.37 here. Hard to read on this chart, but I can kind of zoom in on it, see if we can get there. I don't know if that's any better, but it's 7.5. There we go. Almost can see it. 7.37 come across, and it's 28 gallons per minute. So now we want to go back and actually put that into our table now. 28 gallons per minute velocity through the service line. Okay, next we need to go back to the type K copper water tube chart here for pressure loss per 100 feet. And if we go and take a look, I misread this thing the first time, so you got to be careful, make sure you're on the right column. The PSI of loss for the 1 1/4 inch pipe is actually over here, and I was reading over here earlier. So make sure that you do look at the right place on the table. I'm going to try and zoom this in just as much as I possibly can here. I don't know if it'll help read it or not. It's not very good, but that's as close as I can get to this table. But the value right here is 7.98. Okay, that's PSI. And of course, it really doesn't make too much sense to do 0.98 in this case. Let's just call that 8 PSI because this reading it to the hundredths place is ridiculous for these kind of gauges. Oh, one more thing I forgot. This table is per 100 feet. So we've got to take this value right here, 8 PSI, and we have to multiply the 8 times the actual length that we have, which is 25, and divide that by 100 to come up with our actual value that we're going to put down, which is going to be 2 PSI. So we got 2 PSI, and that's going to be the loss through the 1 1/4 copper pipe for 25 feet. So let's record that value here. Pressure loss in the service line, we said is going to be, see if I can get that all on there. Pressure loss from the service line is going to be right at about 8 PSI per 100 feet times 25 feet, and we decided that that was going to give us 2 PSI over here. And then the pressure loss in the delivery line, if we go back to our original drawing here, we have 1 1/4 PVC, and we're going to have 65 feet of that. So if we go back to filling out our worksheet here, we have to know the PSI loss per 100 feet, and we did have that earlier. If we can find the right table, here it is. All right, here again, let's make sure we're using the right chart here, and we got there, and here's our 1 1/4 right here. So the value is down here. I'm not going to try and zoom in because it's too hard to read with the outline, and the reason they have this darkened in here is because that's where you got to start looking at the speed, because it starts getting pretty close to exceeding the velocity that we want to pipe. In this particular case, we're going to have 4.25 PSI on this 1 1/4 pipe for 28 gallons per minute per 100 feet again. So we have to write that down in this area here. That's 4.25 PSI, and we have 65 feet of it. 65 feet is going to be, let's see, 4.25 times 65 divided by 100, and I think that comes out to about 2.75, somewhere in that neighborhood, 2.75 or somewhere thereabouts. It's going to be close to that loss that we're going to have. This is through the delivery line. And next we actually need to do the water meter again, this time at design capacity. So let's go back to that chart that we had, if we can find it, on the pressure loss through the water meters. And here we go. And I've highlighted this one. For our 28 that we've got on this system with a 1-inch meter, we follow it down and we've got 4.6 gallons per minute. So that's the value we want to record right in here, 4.6 PSI at the design capacity. Now in this particular case, we don't have any of the other valves here, so that's going to expedite things just a little bit. Now we want to take a look at the total pressure loss from the source to the point of connection. So it asks us to add these lines up. We've got 2 and 3/4, 4.6. And if I think we do that math, we end up with somewhere in the neighborhood of about 9, a little less than 9.5, 9 and 9.35 is what I come up with. We want to then subtract any of the pressure that we come up here from the loss from a number 4 up above here, which is the static pressure. So we take the static pressure, and I've actually got this written at the wrong place, 9.35. So let's take the static pressure from up above here, 77.64, subtract 9.35, and we're going to come out with 68.29, a little over 68 PSI for us to work with at the point of connection. That's real important to know that this is at the point of connection. Now, in this particular worksheet, there is one more simple thing to do, and that's to add additional feet of head if your system goes up or if it goes down in elevation. We can do that in this particular case. If you remember back to this, we said that we had a little bit of a rise here, and I think the example called for somewhere in the neighborhood of about a 10-foot rise in elevation to the worst possible location. So that's called the highest possible head in the system. So if we're going to take a look at this, we're going to end up with the pressure change due to the point of connection, highest place in the system, and that ends up being I think we said, what, 10 feet? 10 feet. And 10 feet is going to give us 4.33 PSI. We want to then subtract that from our other line here, pressure subtract for the worst case, and we're going to come up with somewhere in the neighborhood of, what did we have here? 68.29. So we have 68.29. I'm going to subtract 4.33 away from that and come up with about 64. We'll just say 64 PSI. It's very close to that. And then they call here estimate pressure available at worst case 2/3 of the total, line 22 times 0.76 PSI. And we're going to come out somewhere close to about 43 PSI. So those are the two factors that we have to work with. Just review then, we've got 43 PSI and we've got 28 gallons per minute. And those are the two things that we have to work with that will shoot us off into the rest of our irrigation design, which we'll take a look at designing valves and circuits to do individual zones for next week.